Good afternoon to all. Dear friends, in the last few lectures, we have covered many topics in the digital electronics. So yesterday, we have finished the half adder and full adder circuits, as well as half subtractor and full subtractor circuits. So half adder or half subtractor, they are used for addition of two binary digits and subtraction of two binary digits. That means one bit addition or subtraction can be done using the half adder and half subtractor. On the other hand, when you want to add the 3 digits or 3 bits, the half adder circuit is not sufficient, and for that purpose we will have to use the full adder circuit. Similarly, for subtraction of 3 bits, half subtractor is not sufficient, and we have to use the full subtractor circuits. So this is all that things we have learned in the last few lectures. Now today we are going to learn the Boolean algebra. Before studying the Boolean algebra, we know in the last lecture we have studied the De Morgan's theorem and the basic logic gates. So these are the fundamental requirements, prerequisites to understand the this Boolean algebra. We know what are the De Morgan's theorem. Complement of the sum is equal to product of the complement is equal to product of the complement, and the product of the complement is equal to sum of the complement. So these are the two De Morgan's theorem which are very useful in simplifying this Boolean algebra. So this Boolean algebra it is in the digital system. So digital signals can be either be low or high. So we know what is the digital system. Digital system is the system in which signals can be either low or high. So we can denote the low signal by 0 state and high signal by 1 state. And a number system based on this digit is known as the binary number system. So the number system which is based on 0 and 1, because here there are only 2 bits or binary digits. There are only 2 symbols that are sufficient to represent any number. Therefore, the base of this number system is 2, and it is called as the binary number system. So, in the 19th century, George Boole developed algebra for manipulation of these binary variables. So, we know the algebra for decimal number system. So, in the decimal number system, we have addition, subtraction, multiplication, division. And there are some rules which we will have to follow in the algebra, decimal algebra. So similarly, this George Boole developed algebra for manipulation of these binary variables or binary numbers, and therefore, as its name is given as a Boolean algebra. So this was named as a Boolean algebra because it was first developed by the scientist Boolean, and therefore this is its name is given to that algebra. So this Boolean was a mathematician, and this Boolean algebra is the mathematics of digital numbers or digital systems. So this system, this Boolean algebra is used to study and analyze analysis of logic circuits like computers, calculators. So nowadays all the digital electronic circuits uses this Boolean algebra functions. So they are developed on the basis of Boolean algebra. So Boolean algebra, it is the mathematics, in simple words, Boolean algebra is the mathematics of binary numbers or binary digits. In a simple manner, it is the mathematics of binary digits, or it is the mathematics of bits. So, and it was developed by Boolean name of the scientist, and it is very useful in the circuits of computers, calculators, or any modern device that we are using today. So Boolean algebra is very important because all the digital electronics is based upon this Boolean algebra. Uh, so here are some laws uh, that are associated with the Boolean algebra. So the first law is the commutative law. So the first law is the commutative law. Now we know the commutative law for the decimal number system also. What is the commutative law? The order in which the variables are odd makes no difference. So odd means if the two variables are applied to the OR gate, if the two variables are applied to the OR gate, and if the order of these variables is changed, it will not make any difference. It will not make any difference. So this is the statement of the this law is called as the commutative law of addition. So this commutative law of addition is also applicable in the decimal number system also. So in the decimal number system, if you are given two numbers a and b, and if you alter the variables, if the order of the variables is changed, so there is no change in the sum. So similarly, here the order in which the variables are odd means they are added, because OR gate has a function of addition. OR gate has a function of addition. So if they are odd, makes no difference. So let us take the example. Suppose this is the OR gate, which has the variable a as the input, b as the input. So the output of this OR gate is a plus b. The output of the this OR gate is a plus b. So whatever the inputs you use to the OR gate, the output will be a plus b. So it is called as the OR output. Now take this second circuit. So here the order of variable is changed. So the first variable is taken b and second variable is taken a. So it is a b plus a. So it is the b plus a. So b plus a, and it is ORed. So again, depending upon the value of a and b, the output y will be produced. So if you put value of a and b for both these circuits, the output result will be same. Therefore, a plus b is equal to b plus a, and this is the called as the commutative law of addition. So the order in which the variables are odd makes no difference. जर आपण या व्हेरिएबल्सची ऑर्डर आपण चेंज केली तरी पण त्याच्यामध्ये काही फरक पडणार नाही. इट मेक्स नो डिफरन्स. बट वेन वी ऑर्ड, आपण जेव्हा त्यांची ऑर ऑपरेशन करतो त्या व्हेरिएबल्सची, when we make the OR operation on that variables. So this is called as the commutative law of addition. Now this law is applicable in the decimal number system also. So in the decimal number system, if you take two variables, any two variables a plus b, it will be equivalent to the b plus a. Suppose the first variable is 4 and second variable is 5. So 4 plus 5 लिहिणं काय किंवा 5 plus 4 लिहिणं काय, one and the same thing. Both will make the sum as 9. So it makes no difference. So this is the commutative law of addition. The same law is can be applied to the multiplication also. So the multiplication is also commutative. So but the multiplication is denoted in digital electronics by the AND gate. So this is the AND gate, a dot b. So a dot b means a into b. So AND gate gives the multiplication operation. So the order in which the variables are ANDed makes no difference. Again,